we started discussing about the notion of process or task in operating system and what are the different data structure that is available in order to manage this particular process or task. More specifically, we tried and understood the process control block as a data structure. What are the constituents or what are the elements of this process control block that will enable the scheduler, or in a way that will enable an operating system to understand the existence of that particular process in order to get it defined or in order to get it managed in the process of process management or task management, right? So this was the discussion that we started off last time, where we understood basically with a process, the concept of the process, the state diagram, then data structure as process control block. What is the process? What is the? We were discussing about the context switch. We will continue discussing the context switch in the today's session also. Then we'll discuss how does the scheduling processes would take place and what are the different operations those are being made onto the processes by an operating system. So these are the contents. So let's revise. Like, process is nothing but it's an executable entity, which is a self-sustained entity into the memory, which has got everything that with which the operating system can process that particular execution portion in the memory, right? And that is what it's said to be as a program in execution is called as a process, okay, where process execution must progress in a sequential fashion. So whatever sequential fashion that is being referred here, it is just mean like the state transition of this particular process happens to be one after another. Okay, and that is what we mean to be as a process execution. Fine. So anything that is expected to be executed with a single core architecture is expected to be done in a sequential fashion. And that's what it is being written, that the program in execution is the process and process execution must progress in a sequential fashion, right? So as we also understood that in order to understand the existence of a process, the operating system finds a data structure, and that particular data structure has got a typical, or that particular data structure has got a typical section that's called the text section, program counter, program register, processor registers, stack area of the memory, then data section that contains the different global variables, and the heap that contains for the memory management. Then we understood that program is a passive entity which is stored into the disk, as well the process is an active entity. Okay, that means last time also we have seen that if I have got some program into the memory, that not essentially to be executed by the processor, or executed or can be executed by the scheduler also, unless and until this is not being referred one, isn't it? And a very simple example that I wish to quote at the moment is when we are doing two operations in our normal or in our normal desktop operating system also. The two processes that we do, or the two actions that we do, is delete and shift delete. Is it not? So what happens with the delete? With a delete, the file or a folder, whatever content that you want to delete, that gets resided into the recycle bin, right? And when you go with a shift and delete, that content even doesn't find its place into the recycle bin. That's which is called as a confirm delete, and only this delete that has got contents into the recycle bin. How that is related to the discussion that we are making at the moment? When we have a content or a file into the recycle bin, have you ever tried double clicking it to open it? Will it be opened ever? Will that be opened directly from the recycle bin? And the answer is no. We will have to restore back. Is it not? We'll have to restore it back. So does it mean that that particular application or any file, when it is there in the recycle bin, it is not residing into the memory? Yes, it is residing into the memory, but that is not active. That is always being a passive one, because the scheduler doesn't get reference of any of the data, any of the attribute of that particular file, folder, or whatever application that you deleted, which is being there into the recycle bin. Scheduler doesn't get any reference of that. And that is the sole reason why we are calling that the program is being there into the memory, It is there in a stored onto the disk. It is not deleted from the disk, but unless and until you don't restore that back to its original position or restore back to the original memory location, original drives, it will not be executed at all. That means in order to be executed, in order to be ready to be executed, what it expect? It expect that the program attribute should be in place, and these particular attributes or these particular attributes of the program should be known to the scheduler also. And this is what an example which I'm trying to tell at the moment, that when you have got any piece of code or any file or any application in the cycle bin that is there in memory but does not get reference to a scheduler, that's what it cannot be executed there itself. You will have to restore that back to an original drive, original location, and after that original location would now, there you have got different processes, you have got different threads, you have got different tasks which are basically getting assigned by an operating system, and then scheduler of an operating system gets to know that this is to be opened in this particular way, or this kind of operations are expected to be performed onto it. So unless and until operating system scheduler does not understand the existence of any program, that will not be of any use. And that is what it is not only expected that program should be resided into the memory, but it is expected that the existence of that program in the memory should be linked, should be known, should be referred to the scheduler in order to get it executed. And that is what we saw last time also, that program is a passive entity into the stored disk, while process is an active one. Getting my point? So this is what we need to understand at this particular point. So this particular program becomes process when executable file loaded into the memory. It's as simple as this. Then we understood that execution of program started via GUI, mouse click, command line entry of all its name, etc. is basically referred to be as in different processes, right? One process can be of one program can be of several processes. That we have seen last time, even with an example of Control Alt Del. For an application, you have n number of processes. You have got n square or n into m kind of threads that those are going to be there. So all these activities that we have seen last time itself. Okay, fine. Am I audible? It shows my internet connection unstable. Am I audible?
Yes, but for a few seconds you are not audible.
Okay. Because it is reflected to me through my internet connection. That's what I wanted to confirm it. Is it now audible and visible clearly?
Yes, sir.
Okay, fine. Thank you, Devdutt. So continuing over that, like this particular diagram we have seen in the reference of the different constituents of this particular process control block, as we called it, text, data, heap, service, and this particular stack, right? So moving ahead, as we know, the process, as we say, it's an entity in execution that is known by a scheduler of an operating system, has to transverse or has to be there in certain states. Means the journey of a process from creation to the termination would undergo through different steps, undergo through these different stages. And those stages are referred to be as the process states. Okay, like for example, when you are creating a process, that process is said to be there in a state called as a new. Right? You can refer this diagram as we discussed. When process is just created, it is being said to be as in the form of the process called as a new. Then when process is running, when the process will be running, when everything that it has got and it is ready to run, then only that process would be running. So when actual process is running, means process is running by the CPU, then we say that the state of the process is running, that is instructions are being executed in that. Waiting in a sense that we saw that the process is waiting for some event to occur. What kind of event? Any kind of event. It might be like exception, it might be an external interrupt, it might be some event for which you wanted the synchronization to be met in your application. So n number of events, even it might be some resource, it might be some turning on and off of some of the resource which you wanted to link to your particular continuation of the program. I mean, so many events, so many things are there with which the process actually can be there in a waiting state. And unless that is not being received for what it is being demanding, the process would continue to be there in a waiting state, as you can see here. And once that process has received something which is waiting for, that particular process would definitely be converted I would say transiated to the state called as an ready. It will not be directly there in running, as we saw last time, right? So waiting is a process when process is waiting for some event to occur, and it is said to be ready where process is waiting to be assigned to a processor. See, there's a difference. Waiting to be assigned to a processor is completely for by the virtue of scheduler, isn't it? And waiting for some event to occur, that means in order to just get a process to understand that something has to occur in order to continue. Last time I have given an example, right? Like we have got some communication task, or we have got some flag that I can use. For example, if I'm defining in my application, if I'm defining some variable, global variable, let's say, like for example, int signal. This is a variable that I defined, for example. Okay. And signal variable initially after definition, what I did, that signal variable, I made it, or I defined that as a 0. Fine. And in the program, I'm making a provision that if some temperature or some kind of entity has reached to some its threshold value, predetermined value, only in that particular case, that signal that should be made from 0 to 1. And being find signal status as a 1, then only I need to execute some certain section in my application. And that is what is expected to be executed in a sequential fashion. So what I'm referring here, I'm referring some value to be reached at some threshold, means my program or process is waiting for that particular event to occur. And after occurring that particular event only, the signal value that which are initially defined as a 0, that would be becoming 1. And after becoming 1, if I just make it, if signal is equal to 1, then if I'm making some loop or making some further execution of the process, what I'm doing in a way, I'm asking my process to wait for something to happen. Getting my point? So this is in a way referred to be as a synchronization itself. Getting my point? So when process is waiting for some event, it is an waited one. There's a difference, as I said you. Process to be waited for, to be assigned to a processor, that means a scheduler, and processor to be waited for an event to occur. I think this particular discussion is pretty much clear to understand this particular states. Okay. Fine. Then the last state that it happens is terminated, that process has finished its execution. Fine. Okay, fine. Now you can see this particular diagram where it's clearly given that new process after creation that would be admitted into the system and that would become ready. Because nothing is being waited, nothing is being expected. Only it is being expecting that its turn for execution from the processor to be there. And that's what it is being there into the ready state. Now ready state, when that particular, any process is, let's say, depending on the scheduling algorithm, any process set to be executed, then it would change its state from ready to running one, right? So when the state is running, it might change its state because of either interrupt. When interrupt happens, then ISR has to be executed. So that particular currently running that process or task, that has to be migrated into ready, isn't it? Because it has to wait further. It has to wait further for this particular task to be assigned by the processor. That's what it has to be going into the ready state, right? So one transition possible is running to ready by virtue of interrupt. Second transition possible is running to like waiting, as right now I've just given an example for that particular value to be reached to some threshold level. Okay, so until that value reached to a threshold level, the process would be there in a waiting state. Once that particular value has reached to that level, when signal value becomes from 0 to 1, for example, then in that case, the process would be migrated to ready, will not be going to running, because some already process is running into it. Some already process is running into it. So it has to be there into the ready state. And if after that, if that ready state is being there, and if that process happens to be high priority, then according to scheduling algorithm, the low priority process would be preempted and then high priority process would be there. Okay. And then once this particular running process has got everything to over, it is nothing to be waited, nothing to be interrupted. Then once it completes its operation normally, when it terminates its operation normally, then it would be there into the terminated state, that is called as an exit of it. Okay. At this particular point of time, I want you to understand the state transition very meticulously. The sole reason being, like whatever the mu cost to experimentation that we are going to do, The complete experimentation, the total experimentation is based on this particular state diagram. The mucos2 also has got this state diagram with it, where this particular mucos2 state diagram states are different. What are the different states? Instead of new state, it calls to be as a dormant state. Means the task or process is being there into the memory, but scheduler doesn't get referred to that. It's called a dormant state. Okay. Then when it is being there, when it is being the schedulable, when the task is schedulable, means everything it has got to schedule, then it will be there in a ready state. Then after ready, it would be there in a running state. After running, it would be there, or the second possible state can be a waiting state, or it can be an ISR state, and then it can be an exit state. I mean, exactly on the parallel lines, we have this particular states of a mucos2. And once we see this mucos2 states, you would get to know that there are different APIs which are being written onto that particular transition diagram. And these APIs we are supposed to make use in our experimentation in order to validate either the task communication, or in order to validate the interprocess communication, the timer services, or maybe interprocess communication. So all the experimentation that we are supposed to do for mucos2 is completely rest on this particular process state diagram. At the moment, we are referring this particular diagram to be as a general process state diagram of a general purpose operating system. But in mucos2, we are going to discuss the same diagram only with the different name with the help of this mucos2. Okay, so and that would lay down the foundation for designing an application, that would meet the requirement, of that particular application. Getting it? And that is what, when we are supposed to make use of OS, you have to understand in what way the services are to be taken up. Because when we are using for an embedded system, it's not the operating system that drives the application. It's always the application that drives the operating system services. And that is what we should know, in what way we are supposed to make use of it. It's not like a general purpose where the OS completely drives an application. In the case where in the general purpose OS, you might not ever being known with what is the task ID or what is the process ID that you are running into your systems. But that might not be the case with an embedded system design when you are making OS to be used for it. Getting my point? So I think that is all like we need to understand, even as a differentiation that we'll be following very soon in the next part of this particular course. Okay. So after this particular states, this is process control block. As I said you, this control block name itself is very indicative, right? Block that stands for a memory area. Control is order operation. What kind of control event that is be expected to be done, that we'll see. And what is to be controlled? The process is to be controlled. In what way it is to be controlled? It is to be controlled either for the creation. It is to be controlled either for the suspension. It is to be created. It is to be controlled whether for the resumption. Whatever you are suspended, that also need to be resumed, or it is to be there for the termination, or it can be controlled for an interrupt service routines, or it can be controlled for having the different activities to be synced as for an waiting and then go for the synchronization application. I mean, so many things are being there into this control action. And in order to have this all control action of the process, what we have is the different attributes, those we can see here at this particular diagram. This is definitely not the complete list of attributes. Okay, there are definitely a couple of attributes which are still further there. For sake of simplicity and for sake of representation, only these attributes are being written on there. Okay, fine. So you can see that first starts with the process state. It has to be known because scheduler works on the state of a process. That's what I continuously keep telling you, that in the mucos2, high priority and logical and high priority and ready to run. Ready to run is ready task and high priority. So that particular information, you can say that this state that is running, ready, running, waiting, etc. That ready is also there. So it gives me the state of the process. Then program counter, which keeps the track of execution, as we saw last time also. So it's a location of instruction to the next execute. Then CPU registers for the content of the processor centric registers that we all already are understood in the context switch, or we'll see it very soon. CPU scheduling information that is based on the priority, based on the scheduling queue pointers. This is, as I'm saying you once again, this is a sample set of the attributes which are being given. Okay, it even might need like CPU scheduling information. It might need that what is the expected amount of time for which the process would be running, what is the expected or what is the actual time in which the process has finished its normal execution when it executed last time, isn't it? So I mean, all these are the different information that CPU the scheduling might need to scheduler might need to work on in order to schedule that to the CPU. Fine. So there is a n number of lists which is being available for the scheduler, and it depends on the scheduling policy of it. Memory management information allotted to the process and all that, as I said you last time, the paging and all that comes into the picture as a virtual memory manager. Then accounting information, CPU, percentage CPU, clock time elapsed since start and time limits and all that is being expected to be as an statistical information, because in the debugging process, as we are only familiar with an OS as only as an user one, you are not came across anything of the accounting information, isn't it? Even though when we go for the any like for example, even if our system gets hang at some time, okay, hang is actually not the proper technical word to be used in the operating system. The actual systems never get hang. Only the task switching time is so high that we ourselves are not passionate, or we ourselves don't have that patience to wait for that particular task switch. That's what we call that as an hang. Otherwise, there is no as such term in the technical literature called as an hang. This is a layman word that we are using day in day out, right? So OS hang ho gaya, ya my application hang ho gaya. So there is nothing of that term that happens to be there in literature. Getting it? So I'm sure like when we are using this particular accounting information, when we are doing this control alt delete and all that, we hardly see out what is the utilization of the processor. Or some of us definitely might see what is the utilization of the processor. But after seeing it, what we are doing, is anything that we are supposed to do into that? Let me tell you, yes, we can do so many things in it. Because operating system would allow us to query onto the statistical information of CPU usage, statistical information of the start and end time of the task, statistical information of how many times this particular task has executed or process has executed within that particular amount of time. So all this statistical information can be taken up as an answer to the query functions that we can input. And as a result of which, as a result of this particular query function, we can definitely, after receiving the responses from the query function, we can make use of those responses in some algorithmic way in order to proceed for scheduling of the task, scheduling of the application, or execution, planning of execution of that application also. I mean, this is specifically required to be done when we are talking about a dynamic prioritization. Whenever we are designing an application, we comes with the two mode of operations called as an static prioritization of the task and dynamic prioritization of the task. The static prioritization of the task, as the name itself indicates, that before the task gets executed, its priority is being defined, which is a prefixed priority that will never change. And because of which there occurs the n number of deadlocks and all that conditions might occur. And in order not to get those occurs, we can have, based on this particular response that we are receiving from the query function, we definitely can think of making use of this statistical information in order to change the priority of the task dynamically during its runtime, so that at least for the next part of the execution, that particular problem which are being occurred into the earlier phase, that will not be occurred. And we can make our execution to be as a resilient execution. In spite of the errors that is being supposed to be as an erroneous situations, therefore, because of some certain actions, even that we can make sure that our system, our execution would be an our execution could be an resilient one. So we can make that resilient execution of this application also. I mean, so many things which are being there into this accounting information, which we are definitely going to understand in the purview of MuCOS 2. But at this moment, I want you to just make, when I'm going to discuss the MuCOS 2, I'm just going to discuss the facts out of it, because this chapter is related to basics of operating system, right? And on top of this, we are going to discuss for the MuCOS 2. And during that, I'll not iterate or I'll not just recap any of the things that we are discussing here as an basics of it. That's what I want each one of you to just, only 19 are there today, but each one of you to just make sure that you understand what uh, I'm talking at the moment. Okay. Then IO status information, IO device allocations and all that, that is also being there as a part of it. Okay. So this process control block happens to be one of the entity which is being taken by scheduler in order to migrate the process from one to other state and continue the process execution. This is what last time we have seen. We have seen that these two idle bars, which is being there in the process P0 to P1, right? So you can see that this particular P0 to P1, now once process P0 is executed, it has got some system call. It goes the call to the context switches, after which it the process P1 would be executed, process P1 executed for this amount of time. Again, some system call has occurred or interrupt has occurred. It has to restore that back to the control for the PCB 0, like process control block 0. Then it reload the states from process control block 0. Then it will start executing process control block or this particular process 0, and then you can execute it. Getting it? And as we discussed last time, that this idle states, these two, doesn't contribute anyway to the functionality or not being so useful as per the application execution is concerned. That is what, as the minimum the things that you can maintain there as a context switches, it's good. In the latter part of execution or latter part of explanation, this particular point is being there in the consideration. Okay. Please read this particular statements for a while. You read it for a minute, I guess. Context of a process represented in the PCB. Now, what do we have the representation in the PCB? The processor registers, right? Program counters, states of that particular task, the stack itself, the heap, that is memory related information, the statistical information. So these are what the attributes which basically require to control the execution. So everything that is being there in the PCB referred to as in context. And that is what I need to store that particular context from one to other when it's migrate from one to other. And that is what we call to be as a context switch. Okay. So context is a process which is represented in the PCB. Then context switch time is overhead, as even last time I have given an example also. Context switch time is an overhead. The system does not, or system does no useful work while switching. Obviously, right? It's an housekeeping kind of operations. The more complex the OS and the PCB, the more complex the OS and PCB, longer the context switch. What we want this context switch times to be less. We want this context switch time to be faster one. Okay. And let me tell you that embedded applications, since the RISC architecture has dominated the embedded systems, or since the ARM, advanced RISC machines, have dominated the embedded system, and as this architecture has got a larger register files with it, like ARM LPC 2148, as we are going to make use, it has got around 16 registers each of a 32-bit, which could be operated as around many registers across the different banks. And by virtue of having a larger register file, operative register files, which is more in numbers, more the context that you can have stored into those registers, and being it stored and restored from the CPU register, which is very own memory, local memory to the architecture, local memory to the processor core, the amount of time that will be required to switch to and from that CPU register is highly negligible. And that is what, even though the context is more, you can expect that the context switch time would be very less. So context would be switched very fast. Context could be switchable very fast. And that is what, since the RISC architecture or ARM architecture or the Cortex architecture started dominating the embedded system design and development, most of the developers start making use of an operating system. because they are not having fear now that larger context switch time will be required, and that would be an overhead. So that amount of execution time would be lengthened. So that kind of risk is not being found into the today's day of this embedded system when you make use of ARM architecture. That is what ARM or the Cortex M0, M1, M2, or Cortex A, R, all these kind of profiles has got large number of register files. And that is the beauty where the context switch time can be leveraged, can be slowed, or context switch time is very fast. Okay, and that is what the reason where operating systems are being more seated on nowadays with an ARM architecture. That is also one of the reasons, and I take this opportunity to make you aware at this moment itself. Okay, because in the port files, we have seen that OS underscore CPU underscore A dot S, we have got multiple instructions called LDM and STM. Those instructions has gotten capacity to store and load n number of registers from the memory or from the stack in one clock cycle. And that is what the beauty of having these particular instructions of the architecture. Basically, these instructions in the architecture, that's called in system register instructions. System, that stands for operating system registers. And those are extremely beneficial as far as the OS incorporation, OS porting into the architecture is concerned. So many things are being there. So during the porting, what are the 5 rules or 5 general rules that architecture should follow? I would add 6th rule into it. If architecture has got more number of workable, more number of general purpose register files, then the context switch time should be will be very low, and for that it would be advantageous to have the OS switching time, the context switching time to be very less. So we can have the sixth addition among the 5 which is being stated over there as a 6th addition by virtue of the today's trend in the embedded systems. Fine. Time dependent on hardware support. This is what I was talking about. Some hardware provides multiple set of registers per CPU. That means multiple contexts are loaded at once. Again, it shows my unstable connection. Okay, now it's okay. It like, this is what I tried and narrated with a single set of CPU registers. If I have got the different set of CPU registers, okay, how many of you really at the moment agree with me that processor or controller can have multiple stack pointer or multiple program counter? Till now, whatever the architecture that you might came across or might be known is said to have only a single program counter or single stack pointer. Do you know an architecture where we have got the multiple stack pointer and multiple program counters? Ranjit, what is this sometimes not? Okay, okay, okay. It's two, you are written it at 234. Okay, fine. So in response to my question, am I audible or my voice is clear? That is your answer. Okay, fine. Now I ask you the new question that have you come across in architecture which has got a multiple program counter or multiple stack pointer? You can definitely refer it onto the Google, but not at the moment. At the moment, my question is, do you aware or not? The answer can be digital, yes or no. Okay. Now the next task in front of you is you are supposed to find out an architecture which has gotten multiple stack pointer and program counter. Okay, because Some hardware provides multiple set of registers per CPU. Okay, and multiple context loaded at once. And by virtue of having multiple set of registers per CPU, you can definitely have multiple contexts to be loaded at once. And this is what definitely accelerate the context switch time. Getting it? Because the same register is not expected to be manipulated. You have, when you have the duplication or when you have got the separate set of registers, then definitely that would be used for different kind of operations. Getting it? Or if you're not being really known with the register banking, if you're not really being known with the concept called register banking, I want you to refer the concept of register banking in the hardware. Okay? Or if you're not being really known with the concept called as a windowed register or register window, then I want you to find out the concept called register window. And this particular concept you're definitely going to understand from the chapter number 5 of a famous book called as an Advanced Microprocessor by Daniel Tabak. There's a book called Advanced Microprocessor by Daniel Tabak, where the modern architectures are being leveraged in very interesting fashion, where you get to know that register windowing concept. There you go. There you definitely you're going to understand like how exactly the multiple set of registers would provide the better context. Okay, so at this moment, I just make this particular discussion open-ended. I kept this discussion open-ended because we want to exemplify this. Okay, so maybe through Google, we can have an exemplification that which kind of hardware that provides the multiple set of registers per CPU. As I know that ARM architecture has got 7 mode of operations. Okay, and in every mode of operation, it has got its different physical registers that can be used for it. When they are switching back and forth, not from all, there are some banked and unbanked registers. So especially for the banked register, R8 onwards to R13, R8 to R13, these particular registers are banked across the different mode of operations. And these different registers, when you make use into the context switches, according to the mode of operation that you want the underlying applications to go, there would be a different set of registers available to it. And when it has got different set of registers, definitely the operation would be faster. This is not different than every task when it has got own stack. What is the result? When you're not sharing a stack among the different tasks, and when every task has got its own stack, what does it mean? That you don't need to manipulate the common stack for sharing among all the tasks. So doesn't it save the time? It's as sure as that. That is what when you have got multiple set of registers, if you could map those multiple set of registers to, when you can map it statically to the different processes, then nothing like it. I mean, that is the best way where you can understand, or that is the best way where you can make use of the architectural support of hardware in order to accelerate the task switching by making use of an operating system. And this is something which is what leveraged in most of the multi-core architectures also in the today's day. Okay. These are some exemplary representation from the Linux systems. I want you to just read it. There is nothing so special onto it. So like for example, PID, T_PID, that is referred to as a process identifier, or it is represented by the C structure called task_struct. In Linux OS, you can see that task_struct is the data structure that is being given, and task, that means it is meant for the task. Okay. Then you have got PID, that is process ID, long state, that is state of the process. Long is the keyword, or long is what basically the type of the declaration that I might go for the state. You can imagine that there could be n number of states that this process would undergo. Unsigned integer, that is a time slice. What is the scheduling information? How like what is the time slice for which this particular task, when this task is started, when it will be ended, after ending this particular task, what is the next task that is being scheduled? So this unsigned integer that is being given as a time slice in the number of ticks, or maybe directly the time itself. Then you have got the task struct as a parent process. Then you have got the head children process. Then you have got the different files that is opened or you have got this particular memory management struct which is being pointed by this mm. I mean, this is an example of the, I would say that PCB that is being maintained into the Linux. And when I'm saying it's a pointer, it further points to the different data structure. So there happens to be a linked list. Sometimes this linked list may be a singly, or sometimes it might be a doubly linked list. It depends on what kind of scheduling that processor would need to have. In many cases, doubly linked list, in order to link the different TCBs, are being more preferred for it. I'll let you know the reason for this doubly linked list. You using or making use of the doubly linked list in order to link the different task control blocks or different process control blocks. Okay. You can see that this is an representative information that is being given to migrate from the struct task, that is process information. These are the different TCBs or PCBs, you can call 1, 2, 3. So this might need to link, or that might need to change from one to other. In the process scheduling, the purpose of process scheduling or task scheduling is maximize the CPU use. That's it. Less the idle time of the CPU, more is expected to be referred as a throughput of the CPU. It's as simple as that. If I go back and just see this one, if I can reduce the idle time, means processor is involved in some of the other tasks, not in the housekeeping operation, for example. Then in that case, you can see maximizing the CPU usage. So maximize CPU usage is the primary task. Quickly switch process onto the CPU for time sharing, for example. This is the primary purposes for which, as I said you, that this presentation is basically for general purpose operating system. Okay, where, as I said you, that GPOS or general purpose operating system is always have got the design role, or always has got a key design aspect of maximizing the throughput. How many tasks, how many processes could be executed per unit time? Maximum the number, better the throughput, and better the performance that is being referred for it. That's what I told you many times, that operating system usage from the developer perspective are different. Each developer would like to see operating system from the different perspective. Okay, one of the perspective for GPOS is maximizing the throughput. How that can be done? It can be there with quickly switching the processes onto the CPU for the different time sharing purpose. As simple as this. Okay, so basic role is to maximizing the CPU usage by having maximum throughput. The process scheduler selects among variable processes for next execution on CPU, right? So we call that as a scheduler or process scheduler. Maintains scheduling queues of the process. What that scheduling queues have? The job queue is there, ready queue is there, device queue is there. What job queues would say, or what job queue would contain? It contains that it's set of all the processes in the system, including ready and non-ready states also, or including ready and new states also. Ready queue, set of all processes residing in main memory, ready and waiting to execute. That is what, when they are in a ready state, they are ready and waiting to execute. And device queue, the set of processes waiting for an IO devices. Means whenever the resources are getting shared, whenever the resources are being used, and few processes are being there intermittently used to share the resources. When these particular, what are the different processes which has got a dependency on the external devices, IO devices, that is also one of the queue that is expected to be maintained on that. Okay, and then finally the process migrates among the various queues. How it migrates around the various queues? Let's see this. The representation of the process scheduling happens to be when you have got the ready queue, CPU can schedule it. Once the means from ready, it will be there in a running state, right? So in the running state, what happens? It will check for the IO request. Okay. Then if IO request is being found for the running state, when IO request is being found for that process, it will put into that particular IO queue, isn't it? When the IO operation have been performed, then it would go to the ready queue. And once that ready queue is being there, see, when we say it's a queue, what does it mean? What is the data structure, or what is the ordering information in the queue? It's always a first in, first out, is it not? When I'm saying it's a queue, it's always going to be a first in, first out. Let me check. Are you with me? Are you with me?
Yes, sir.
Let's do a very quick exercise. I want all of you to just uh, start your video for 1 second, 2 seconds. Yes, there's a nice background. Neeraj, Tanay. Yeah, I could see. Hussein. Yeah. So shall I consider only these are there in the, in the meeting? It becomes like, yeah, Viraj says yes. Okay, fine, fine. I believe that most of you are there with me. So I can just go. Okay, you can, if you wish, you can have, or you can just, yeah, Govardhan, Rohan, I could see you. Fine. Thank you. Thank you. Okay. Thank you for responding. Okay, fine. Let's complete. Yes, Viraj. Yeah, I could see you. Someone has written something in the chat. I'm also in. Yeah, yeah. Ranjit, you are also in. Fine, fine, fine. Sas, yeah, Tanay Chordia, yes. Sometimes it becomes a question like if only one is being talking too much and no response from the side, then it becomes the matter of concern, right? So it just becomes a Dobitious state. My state from running goes into the state that we declare as an Dobitious state, where some doubts are being when I started getting doubts whether someone is listening or not. That is what I did this exercise. Okay, fine. Okay, fine. So from ready queue, the highest, depending on the scheduling policy, from ready queue, the CPU would take that any task from this particular execution. So I was referring there here meaning as a queue, that is a first in, first out. Okay, fine. So once the task is being running, there can be the different options where the task might either go with a natural termination in the sense that it will not be running, no longer it will be running. There might be different options. What are the different options? Those are being given there. And that is what referred to be as a representation of the process scheduling. At what different instances this process would be scheduled from one state to other state. This is what meaning of this particular diagram that we call as a representation of the process scheduling. Okay. Yeah, I'll very soon wind it up. Fine. So once the task is running, when the task is running, I can say that when it gets IO request, that will no longer be running, right? So it has to put into the ready once again. But before that, it will be there in a waiting, right? So after waiting, whatever it has been received, it will go into the IO queue. Then if it receives the information from the IO queue or response from the IO queue, then I can definitely say that it will be there in a running state. The next instance which will make the process or task deviate from the running one is time slice expires. Task or process runs, it's supposed to run for some amount of time, and after which that time has expired, time slice has expired, so it has to go to the ready state back, right? One more incident that can be there, like for a child, it has to, or that particular task which is running, process which is being running, okay, it has forked a child in the sense that it has created that particular child, okay, and that particular child starts executing, but it has to come out of that particular execution because original, though the parent and child process shares the same memory area, I repeat my statement. Though the parent and child process shares the same memory area, the execution instances cannot be the same one. That is what I wanted to highlight out of it. That's what when, for example, parent process runs at this moment in the running, and in the running state, if some parent process has to create some particular child thread or child process, then it has to come out of the running state. It will create that particular child. Then child would start executing, but it will not get executed directly from the CPU. It has to put into the ready state. And then again, once the turn for that particular parent process would be there, then instead of running that particular parent process, the area of memory area being shared same for parent and child, this child will be executed on. As simple as this. And next option is when the process is running, it can be interrupted. And once the interrupt has occurred, it will go to the ready state. And once that particular event or once that particular process would get chance from CPU to execute, then that ISR would be running on it. That is what we say it's the representation of the process scheduling. This is in general which is being given for the general purpose operating system. Okay, fine. So these operations on the process, like the process creation, termination, and all these particular details, I think we have fairly covered these particular details, but still this is the last slide. So I definitely would make this particular things in a recorded form, and I'll just pass on to you. Okay, already we have discussed all these particular things. When the parent process creates a child process, which is in turns creates another processes, forming a tree of process, and this is what we refer to as a tree of process. Okay, fine. Okay, respecting the time that you all have, this is what the attendance. I'm expecting 19 to fill up this particular attendance. Is there any special day? Any campus, any placement, any orientation? Devdatta, do you have any idea for that?
No, sir.
Means nothing is there of that order, no?
Not that I remember.
Okay. Because those who are attending would definitely be benefited. Otherwise, those who are not attending, I think, yeah, principal global interviews are there. Okay, Tane. Okay. And is it a no criteria company? Okay. Yes.